Hi, my name is Kimberly. I am a second year electrical engineering student. And this past summer, I've been working on designing a high temperature ultrasonic transducer that is used for non-destructive testing. So non-destructive testing, or NDT for short, is used by a lot of different industries, such as power, chemical, petroleum plants, for various applications, one of them to test the integrity of their equipment for any defects without causing damage. Transducers are a kind of instrument that is used for NDT that takes some change in a physical quantity and converts it into an electric signal, which is then analyzed. An ultrasonic transducer is a special kind of transducer that uses ultrasonic waves to create that electric signal. Over the past summer, we've been working with AMAG, a company that supplies NDT devices to these industries. However, on the market right now, high temperature transducers are only operable to up to 400 degrees Celsius and break down rather easily. Our goal was to design a 3 megahertz wideband ultrasonic transducer to continuously operate from room temperature up to 600 degrees Celsius. We also aimed to minimize all the internal stresses so we can extend its lifespan to up to 2 years. Some basics into how ultrasonic transducers work. I hope you can see my cursor, but there's an element here called a piezoelectric crystal that basically converts the electric signal into a ultrasonic wave. So an initial pulse is sent out to this crystal, and it creates and transmits an ultrasonic wave that goes into this test specimen, bounces off a crack or the back surface. The reflected wave is then absorbed by the crystal, which converts that into an electric signal that is sent out to a computer that is processed and analyzed. Other important features include the zirconia backing, which damps the reflected wave to improve our signal resolution. These alumina insulator parts ensures that there's proper electrical connections within our transducer. These thin silver foils allow the wave to properly transmit into our test specimen. As we know, waves travel at different speeds through different mediums, so it allows for improved wave transmission. And then a stainless steel housing holds all of our components together and keeps external particles out, while also improving wave transmission by acting as what we call a matching layer. So we believed it was really important we model the internal stresses of our transducer first before we moved on with building it. And we decided to use finite element analysis using this program called COMSOL Multiphysics. Finite element analysis is when you take a model and divide it up into thousands and thousands of little elements. Then this program solves a bunch of mathematical equations to predict the behavior of these elements, then connects the elements together so you can predict the behavior of the overall model. So what we did was we ran an axisymmetric simulation since our transducer was symmetrical. And what we included was like a boundary condition to mimic our transducer connected to a pipe that would heat up to 600 degrees Celsius over 3 hours. We thought that this was very important because the internal stresses due to thermal heat inside the transducer were going to increase, and we had to make sure that the materials didn't exceed their yield stress and break down during operation. Also, we needed to ensure a 120 megapascal load on our crystal for effective wave transmission. As you can see, here are two of our possible designs. This was our first one, and we noticed that there were really high stresses all the way to the gigapascal range, which was unacceptable. So we used some basic stress decreasing techniques, I guess you would say, such as adding fillets to the sharp corners, adding in some air gaps for more expansion. It helped somewhat. However, we noticed that there was some really high stress in our crystal, which was not acceptable for proper wave transmission. So what we did was we went back to a very simplified model and realized that our crystal was being restricted from expanding radially. After modifying the contact pairs and the simulation settings, we found a way to model our transducer to maintain normal contact between components, but still allowed the crystal to expand radially. Some issues we're facing now is we have some inaccurate stresses based on the forces that we're applying. As you see here, it's really high in, this is the steel component, and really low in our crystal, and that would not work for our wave transmission. So we believe that we need to continue manipulating our contact pairs and simulation settings until we have a model that is more accurate and have accurate stresses. After we've completed modeling, we're going to move forward with building and testing our transducer in the lab. at high temperatures to determine its flaw detection capabilities. The completion of this project will benefit a lot of different industries that use NDT by providing more robust and reliable results. By having a transducer that works over a wider range and continuously at that point, allows you to detect any defects quicker, allowing you to keep a safe environment in your workplace. Also, by having an extended lifespan, it minimizes the number of replacements you need to buy, thus allowing these industries to use more economical and sustainable practices. In terms of the world of NDT, this can act as a basis for future ultrasonic transducer designs that is to be used at even higher temperatures or for even longer periods of time, thus increasing the already numerous applications that non-destructive testing is used for. And that is everything for me. Thank you so much for listening, and I open the floor to some questions.
All right, thank you for the presentation.
Oh,
thank you for the response.
I appreciate
so we'll ask the judge to maybe do raise hand, and I will address them for the question, if you have a question. All right, and I do apologize if I mispronounced the last name of the professor. So Professor Amami, do you want to go first?
Well, thank you. Just a quick question, Kimberly. I'm curious what kind of software you use to analyze the thermal stress concentration.
Yes, so we use this program called COMSOL Multiphysics, and it basically runs simulations where you compare different physics. So what we did was we included solid mechanics. So we inputted all like the Young's modulus, the Poisson's ratio to determine the stress. And then we also paired it with a heat transfer interface. So the program, it took care of all the conductivity with the transducer and the thermal expansions of all our components, and used that to calculate the internal stress.
Oh, okay. Sounds like a very interesting software.
It's pretty cool, yeah.
Great.
Thank you for your question.
All right, now Professor Eleuterio, you want to go?
Yes, thank you. Okay, so Kimberly, thank you very much for your presentation. I gather that that you did a combined structural and thermal finite element analysis.
Yes.
Is that correct?
Yes.
Okay. So so my question is, how did you test? How do you know that what's coming out of COMSOL is correct?
Yeah. So that was something that really took a lot of nitpicking on our part. So these first two models here, what we noticed was we apply a boundary load of 12 kilonewtons downward here. That acts as like a bolt force to keep our transducer in place while it's operating. And that doesn't change. It's continuous over the 3 hours. And so we were thinking that if this force doesn't change and the components inside should not expand too much to cause such a high jump in our stresses, we thought that these numbers for almost 5 gigapascals was inaccurate. So we decided we need to see if there's something wrong. And there was, because of the crystal wasn't expanding, and that's why we had some inaccurate stresses there. However, now we're getting this inaccuracy where this is under a lot of stress, but how are these components not experiencing anything if our load is being sustained throughout all 3 hours? So that's why we believe that if we manipulate the contact pairs and find that optimal simulation setting, we'll be able to create a more realistic stress simulation for our transducer.
So in the end, you actually tested it, gauged it based on experimental data.
In terms of like the stresses inside, do you mean, or?
Yes, and yes, you is that correct? You actually.
I believe this was again like Kelly's project. It was, we kind of like took it on kind of, and okay. I believe they did run some initial tests. I'm not 100% sure if they were able to determine stresses within our transducer. However, we just believe that having these components reach the gigapascal range is way too high. If anything, it should still be up at the high megapascal range.
Yeah.
And so,
But when you say it's way too high, what I'm wondering about is it way too high to be realistic, or way too high in the sense that your design needs to be reconsidered?
we ran through so many different designs. This is just 2 files, honestly. We have way more. And no matter what what design fix we included, they were still reaching really high stresses. And so when we talked it over with our supervisor, he was like, okay, there's probably something wrong with our simulation.
Okay.
Yeah.
Because did you use different numbers of elements?
Yes, we took out
Okay.
some elements, and we tried changing. We had to do a lot of research into the temperature dependence of our material properties as well. Even changing those barely did anything. Yeah.
Okay, because that's always a good thing to do, to just double up on your elements, like increase the number of elements to see, are you asymptoting to a solution?
What do you mean exactly by?
Well, for example, if you just had 10 elements, well, then that's a pretty crude model, and
True, yes.
you get your temperature distribution, you get your stress distribution, you get your strain distribution.
Yes.
If you double that, go to 20, 40, 80, whatever, then are you seeing those numbers, those responses asymptote to a given to given values? And so then at least you can be sure that your numerical system, your numerical calculations are kind of settling down.
When you mean elements, do you mean like when it divides up the model into
Yes.
pieces? Oh,
That's
yes, sorry. I thought you
exactly
meant
what.
components in the transducer.
No,
Yes.
I meant element as in the finite element.
Yes, we went up to the finest possible within our
Okay.
thing, and
Okay,
it was
good.
still showing up like this. Yeah.
Okay. All right. Good.
Thank you. Thank you for clarifying that. Yeah.
All right, thank you, judges, for your question, and thank you, Kim.